hyperbolic identities, which is similar to trigonometric identities. So you need not panic about hyperbolic. And to introduce it once more, hyperbolic functions are associated with hyperbola geometry. Okay, so we have the following functions. Take, for instance, sine h. It's usually represented or denoted with a h at the end of your trigonometric function. Say you have sine. Instead of writing sine s, you write it as sine. That's sine. So sine hx. Okay. If it's cos, it's cos x, tan x, and so on. And sine x will imply exponential x minus exponential minus x over 2. That is actually how you solve for sine x. Okay, so if you're given a function sine x, let's say x is 25. So what are you going to do? Let's just quickly go on the whiteboard. Oh, see you cannot see my screen. Is anybody also? Oh, someone cannot hear me. Can you hear me now? Okay, Talenta, you can see the screen and you can hear me. Can everyone hear me now? Okay, thank you. See you may need to exit and come in again. Probably there's something wrong with your network. You should rejoin. All right. We'll just wait for you. We would not wait. We would wait for you in a way. I just want to share the whiteboard. Okay. So this is what I was saying. Suppose, no, I don't need to come to the whiteboard. So I need to just stay there. I can write it there. CEO, are you fine now? Can you see the screen? I'm just coming back here. So I was saying, if we were given x to be 25, okay, I have an example here, so we'll get it. And then you have cos x will be the exponential x plus. Please take note of the sign. For sine, it's a negative sign. For cos, it's a positive sign, okay? She cannot. What is happening? Why can't you? But every other person can see the screen. Okay, I would stop sharing the screen and I'll share again. Okay. Someone cannot still see the screen. CEO, can you see the screen like this? Can you see a white screen? Can you see this? See you. Oh, Then I don't know what the problem is. Will you want to go out and join again? Maybe that's going to solve it. Or check your network connection because you seem to be the only person here that cannot see the screen. And I actually want everyone to see and follow today's class because I appreciate that you have joined, and it will not be good if you cannot see. Okay, so we have the hyperbolic function of x represented in their exponential form, okay? And then we have odd functions and even functions, okay? And what do we mean by odd functions of odd hyperbolic functions? Odd hyperbolic function would mean when you have signs of a negative x, okay, you're going to be having it as minus signs x. And that you will see a lot of it when you're plotting or sketching the graph. If x it's negative, then it would just imply a negative of the sine function or the negative of the hyperbolic function. If it is even function, the negative of x will not be negative of the hyperbolic function. And for instance, in the case of cos minus x will still be equal to positive cos x. And that applies to cosec. Okay, cosec is going to be the same. Negative x will be positive cosec x. But for others, they would be negative of that hyperbolic function. All right. Now, let's solve this example which I was trying to show you initially. Let's say we're given sine 5.4. Can you guys do this on your calculator? Can you try to solve for 5.4 sine 5.4 on your calculator? I'm giving you 2 minutes to do that. Okay. Just before I go into the solution, I'm saying you should try to do sine 5.4 on your calculator. Do that now in 1 minute. If you're done, what's your answer? Let me know when you're done. Write your answer out. I'm waiting. Okay. But you have converted it, you have expressed it in 4 significant place. So if you cannot do that, you can just look up a video online and see how to use your calculator. You should be having a scientific calculator to do this. So let's go back to expressing it with our exponential function. All right. Someone asks, how did we come about half? The half, don't forget, when you look at the hyperbolic function, okay, when you look at the hyperbolic function, you have sine, it's just here. It's exponential x minus exponential minus x over 2. Okay? And that is where the half is coming from. So we have simply brought out the half and left with exponential x, minus exponential minus x. Okay? So that's what happened here, and that is where that's how we come about the half. So all you just do is substitute the value of x into the exponential function. And when you substitute it, you're going to have it as 110.7. Look at this in 4 significant figures. If I say in decimal place is different from significant figures, okay? Please don't confuse that. So we go to, I believe everyone understands now. And here is the table which we need to sketch our graph, the hyperbolic function graph, okay? So I have populated this table because of time. I would have wanted you to do it, but please, at your own time, try to repopulate this table. I'll show you how I've populated it. I've populated it from here, from this function of x expressed in terms of exponential. All right. So when you substitute values as we have done in that example, let's say I am to compute sine, just need to reduce this. Okay, say I am to populate sine x, sine x would be exponential minus exponential x minus exponential minus x over 2, right? So what I've done is I've substituted minus 3 here, minus exponential minus 3 over 2, okay? And that gives me the value of minus 10.02. So you do the same substitution for minus 2, all right? Minus 2, it gives this value. And you do the substitution for minus 1, it gives this value. And then you do the substitution for 0, it gives this value. You continue to substitute till you have this. If you look at this table, you will discover you have from a range. This is more like a range. Let me delete this, erase all of this. You see, we have got values from the range of minus 3 to 3, right? And if you look at the values for sine, the values actually goes to the negative. The values go to the negative and goes to the positive side. So easily we can sketch a graph. I would want you guys to actually sketch a graph on your own. I know it's there on the slide, but I want you to do this on your own. Sketch the graph of sine x now with these values. Okay, I want you to sketch the graph of sine x using these values. Please do that now. If you're having problems sketching, please indicate, let me know. I want you to sketch the graph of this. Okay, just that. I believe we are all doing that. I need a bigger space here. I'm waiting. Are we done? Have we all sketched that graph? Please tell me when you're done so we can proceed. Are we done? I'm waiting. No one is responding. No one is responding. Are we host there? Are we still there? Okay, not done. I'll wait. No problem. Okay. Waiting. Okay, I think we're taking so long time. Let me just show you what I've drawn. In my own case, I've sketched out the graph of Koch. Okay, the graph of Koch X. And because of the space, I couldn't extend my y coordinate to what is the highest value here is 10.07. So I've assumed this is the highest coordinates, 10.07 here, this point. Okay, don't mind my scaling, it's just because of the space here. Now, what have I done? I'm considering cosh x. What's on the x-axis? It goes from 0 to the positive side is 3 and goes on the negative side to -3, right? Because our range, which you can consider any range, but I've just, this range is enough to sketch my graph, this range, okay? So I've considered that range. And on the x-axis. So what I've simply done is when x is -3, right? Then the value corresponding y value is 10.07. So it's this point here, okay? And when x is -2, the corresponding point is is 3.76, not minus, 3.76. When x is -1, the corresponding y value is 1.54, which is here. And when x is 0, the corresponding value is 1, y value. And that goes on till I get to when x is 3. The corresponding value is 10.07. If you look at this curve, it has no turning point around 0, right? It goes from 10.07 and turns at 1. So this is how the curve of a cosine, cosh function looks like, all right? And when you're done sketching for sine x, you see in its own case, it has a curve around 0. It extends to the negative side. So your graph should be looking like this for sine, like this. Remember, this is 0. Comes like this and goes like this to the negative side. So, and then you do for tanh, tanh also extends to the negative side, and you do for coch, it extends to the negative side, and for cosec, it also extends to the negative side, and for sec, it does not extend to the negative side. All right, please do that as a practice on your own. Now I'm just going to show you how the sketch looks like. This is what I told you about science. This is what I drew just now for Kosh. And we go on for Tange. You see, it extends to the negative side. For Koch, remember at 0, it is infinity. So that's why it does not touch 0. And then you continue for the for cosec, it's also at 0, it's infinity. So that's why it's not touching. And then sec, you see, it doesn't have any corresponding y value at the negative y coordinate. So that's, please practice on your own, and you're going to have a lot of that in your engineering course. Okay, what are hyperbolic identities? Recall your trigonometric identity, where you have, for instance, Pythagoras theorem that says x squared plus y squared equals to z squared, or sine square x plus cos square x equals to 1. Those are your trigonometric identities, right? Now, we're going to be having similar thing with hyperbolic identities. And what I've said is, for each trigonometric identity, you're going to have a corresponding hyperbolic identity. All right? And how do you prove these identities? You can either prove in two ways. One, by replacing your sine function by exponential minus x over 2, and your cos x by the positive part of it. Or that's replacing the trig identities now. Or you use something which we call the husband's rule. Okay, we would see this and see a lot of proof of that in our examples. So husband's rule says the 6 trigonometric ratios, remember your trigonometric ratios, in the trigonometric identities may be replaced by their corresponding hyperbolic function. What do we mean? You can replace them with the exponential function. But, take note of that, but the sign of two sine products must change. Okay? It must be changed. So let's see this example. No, before we see the example, I've tried to put in this table. It's extracted from your textbook, from your recommended test, which is the Higher Engineering Mathematics by John Bird, okay, the 6th edition. So you find this in the textbook, where the trigonometric identities have been represented by the corresponding hyperbolic identities. Okay, look at, for instance, cos square x plus sine square x, which is 1 in the trigonometric identity. You're only going to have cos square x. Now, this is what the theorem is telling us, that the sign of the sine function must change. You see? Can you observe that difference? The difference is in your basic trigonometry, cos square x plus sine square x equals 1, right? But in the hyperbolic, you have cos, that's cos square x. The sign changes to minus, sine square x will be 1. Okay, and also for the second one, the second trigonometric identity, the sign changes to tan. With tan, for cot, you have the sign changes to 1, and all of these applies for all your corresponding trigonometric identities. Okay, please take note of that. Look at the double angles, for example, where we have from negative, when we have negative sign here, the corresponding trigonometric hyperbolic identity changes to positive. All right, and here you see it changes. So you must observe this, and that is how you use the hyperbolic identities to solve different problems. All right, this is in your textbook, so you can always look up that in your textbook as well. Let's see the application of these identities. First, remember we always want to prove our trigonometric identities. So in this case, we want to prove this identity 1 plus 2 sine square x, which is equals to cos 2x. You can start on any side. So, but for me, I prefer to start on the easier side to derive my proof. I've started from the left-hand side. And 1 plus 2, 1 plus 2 sine square x is what? If you go to your identity function, you have it as, or no, you express it with in terms of exponential. That's what I've done. Sine square is this, x, this is x, okay, over 2. Remember, this is a square. It's got a square. I put in my square. All right. You need to expand. You need to not even expand this. So I've not expanded. I've just done taking the square of each element here. It will be 2x. Okay, minus exponential minus 2x over 4. That's what I've done. All right. And what I've done further is to just divide this. Okay. Then I'm left with 1 exponential 2x minus exponential minus 2x over 2. Sorry, I've expanded it. That's why I have a negative 1 there. Okay, and this 1 will be 0, so I'm not going to have this anymore. So I'm left with this value. All right, and if you look at your cos x is what? In this case now, you're having 2 multiplying your x. So that is equivalent to having this. And I said by definition, that's what you have. Okay, so we want to look at another example, which we want to see determine the value of A and B in this case. It's similar to what I've done, but here, since we have been given values for h, why is this happening? So we have the right hand side now is what I'm considering, and it's 4 cos exponential x plus exponential minus x over 2. This is cos, okay, and this is sine. Okay, now simplify this further. You have this. All right, simplify it. You can do that in your rough book. and see if you have the same value. I would always like you guys to confirm all of these solutions. So let me just do that. That will be 2 exponential x plus exponential minus x 2. However, I come about 2, this divides this is 2. And here, that's this part. I think it's fine now. Then this part is, you can have 5 over 2. That's minus 5 over 2, right? Exponential x plus minus times minus is plus 5 5 exponential. In the previous, I'll go back there. Hold on. Let's just finish with this minus x over 2. And that's what I've got here. All right. And then you solve this further. Okay. You're going to have these values. And how do you solve it further? I think that should be straightforward. 2 exponential x minus 5 over 2 exponential x. Like, yes, you look at the ones with like terms, plus 2 exponential minus x, then plus 5 over 2 exponential minus x. You solve for this will be 2, 4 exponential x minus 5 exponential x. Okay, and this will be what? Minus half exponential x. Then this second part, it's 2, 4 exponential minus x plus 5 exponential minus x. Then you have 9 exponential minus x over 2. So yeah, now you want to remember we want to know what a is. And what is a? A is equivalent to minus half, while b is equivalent to 9 over 2. You see that? All right, let's go back. Someone is pointing our attention to something here. Cosh, what is cosh? Cosh should be exponential. Let me write it out. Cosh x is exponential x plus talenta. We'll go back there. I'm here on this slide, so let's attend to what someone pointed out here. Over 2. Okay, this is cosh. And so he was asking, shouldn't it be yes, I have written it as exponential 2x minus exponential minus 2x, right? What's, please just expand. I think the sign error must have come with the expansion. Please do the expansion. If you still don't get that right, in our next class, please remind me. I will show you what is wrong there. But I'm trying to be as fast as possible today. Please note this. If you still don't get it as a positive sign, then point it out in the next class. I mean, do this expansion. Okay. Talenta, you were asking me about one. Which one are you talking about?
On the last slide, sir.
You mean this example?
Yes. Yes, sir.
Yes, I've said. Are you asking for about this minus 1? Okay. Yeah.
Yes, sir. Yes, that
Okay.
minus 1.
Yes, I've told you guys, I've left it as an exercise. I would want you, let me clean all of this. I see some of your colleagues have actually found what is happening there, but I'll leave it as an exercise. No one, that reminds me, no one has asked for a tutorial. So I'm happy it's like all of you understand all we have been learning so far. So I'm happy about that. So what I want you guys to do as an exercise here is do this expansion, okay? And then see if you will be arriving at the corresponding value of cosh 2x, okay? Please do that at your own time. Um, let's go on. And I've also left you with exercise to do. And this is the first exercise is actually similar to what we have just done in example 2. Then try to prove the husband's rule, this A and B, and then I want you to show that tan square x plus